If I do an experiment similar to your lab where I take a thermistor and I have that hooked up in a kind of resistor divider circuit, so I'm able to pull out a voltage from the change in resistance in the thermistor. And in this case, instead of just touching it, I dunk it back and forth between ice water and boiling water. So what I'm effectively providing as a signal is a square wave alternating between 0 degrees C and 100 degrees C. So once I go into the boiling water, now I'm at 100 degrees C, I go back to the ice water, I'm down to 0 degrees C. So in an ideal world, you might have something that follows that temperature signal exactly. But what you might see in your sensor is maybe it has some, I have a different axis here that is kind of my sensor output. And so I might start at this level, and, it might take me a while, and I kind of get up here, and then once again, kind of takes me a while, and I get up here, and it kind of takes me a while, and I get up here, right? So I'm not following the square wave. It's not even a kind of compressed or amplified version of that square wave. I have something that has some dynamics to it, right? And what you may be able to recognize from this plot is I have some first order dynamics in my thermistor in the way I'm measuring temperature. So another example is from my own lab. We're trying to make a little robot jump. And so one of the ways we did this was a robot that was about 4 by 4 by 7 millimeters. It had a little piece of energetic material in the middle and a little wire patterned on top of that energetic material. And when you shoved a current through it, it heated up the energetic material enough to initiate a reaction. And when you did that, you got a lot of thrust out of that pixel of energetic material, and the robot would jump. And we were interested in measuring the thrust force from this reaction so that we could ultimately design a robot to jump in different ways. And so we basically took this robot, flipped it upside down, and glued it onto a force sensor. And when you initiated the reaction, once again, you got a bunch of thrust kind of pointing up, which pushed down on the force sensor, so ideally you'd be able to measure a force. And our expectation is that if we tried to measure that force, we'd get some kind of signal that might look like this, and the duration of that signal might be on the order of a millisecond, maybe less than that. We'd get a peak in the order of a couple hundred millinewtons, for example. And that was our expectation for what we might get out of these force sensor experiments. Now what we actually got was something that looks like this, and the duration was about what we expected, but we got all this crazy ringing going on here. And this is because if I were to crack open that force sensor and look at what is inside of it, I could effectively model that system by a basic mass spring damper. So I have a mass, I have a spring, I have some damping here as well. And so what I'm probably trying to measure here is this distance between the mass, for example, and the ground. And as that deflects based on some applied mass to it, I'll be able to see that change in displacement. And the problem that I encountered is that I incited some kind of resonance in this sensor, right? This is inside the sensor. So this whole thing is inside that force sensor that I had on the previous page. So what I was doing here was inciting that resonance, and that's why I get all of this crazy ringing in my measurement. And obviously that's not what's going on with the thrust, but that is a consequence of the sensor that I was using to measure the thrust. So my point in all of this is that sensors have dynamics, and if you're trying to measure a system, whether it's a micro-robot thrust force or a temperature, you need to take those dynamics into account. So in this class, we're effectively going to be thinking of sensors as a linear system. And for a linear system, the really nice benefit of linear systems is I can have some input signal. Maybe that's f of t is f cosine omega t. And if I know that, then I'll have an output signal where I get a cosine at the same frequency, omega, right? The omegas here are constant in a linear system. but the amplitude now has changed. It's gone from f to some y based on the frequency. So that's saying that the amplitude, kind of the amplification of the amplitude will change based on frequency, and the same thing happens for the phase. And the great thing about this is once I know how this sensor as a linear system behaves for a step signal or sinusoid like this, I can describe effectively how it'll behave for any signal, because I can then create some Fourier series composition to describe that signal, or a Fourier transform as well to think of that signal. Right? But inside, in order to understand how those things change, the magnitude and the phase change, I'm going to think of my sensor effectively as a differential equation. And for a linear system, I can describe that as a bunch of coefficients, and I've used a little an to describe these, as well as a bunch of derivatives of that output. So an term will be the nth derivative, an minus 1 will be the n minus 1th derivative, a1 will refer to is the coefficient for the first derivative, a naught is just the y signal. Those will equal f of t. Right? Perhaps in an ideal world I wouldn't have these dynamics. I would just take away all of these a terms except that first one and just say, y is some constant times f of t, which would be great. But in fact, we do have all of these dynamics, and that's what the rest of this is describing. So that ideal case we would call a 0th order system. The order of my system is going to be described by the highest derivative of the differential equation that I need to accurately describe my system. So n is my system order. So in that ideal system where, for example, I just had this a naught y equals f of t, right? My output y would be 1 over a naught f of t. I have no derivatives in that system, so that would be a 0 order system. If I just had this first derivative, I'd be looking at a first order system. Okay, so let's talk about those 0 order sensors briefly. So I was describing those by this equation right here, where I have a naught y is f of t. Remember, based on my definition that I had on the previous slide, f of t is effectively my input, y is my output here, and a naught is the coefficient on that, so I can rewrite this to get y is 1 over a naught times f of t. Or I could think of this effectively as a sensitivity, so just k f of t, where k here is 1 over a naught, and I'm defining that as my static sensitivity in this sensor. So this static sensitivity, if I think about what this actually means for a sensor, static sensitivity is proportionality between input and output in steady state. And I should have mentioned that previously, right? That cosine thing matching up, where I get a magnified and a phase shifted cosine at my output, that's in steady state, right? I might have some transients before it gets there, but at steady state, right, I'll get some sinusoid at the same frequency, just with a different magnitude and phase. So what this means is if I have a step input, say with some amplitude a naught, then my sensor signal is going to be proportional to that input. So maybe this has an amplitude a1 u of t. Right? So the signal is a1 u of t. It's just a step with an amplitude of a1. And that a naught and a1 are going to be related through this static sensitivity. Right? And the same thing will happen over here for this sinusoid. I'm just going to get an output that's proportional to my input. So now I have an amplitude of a1. My input had an amplitude of a naught, and so now I just get as my output a1 sine omega t. And so once again, a1 and a naught are related by that static sensitivity. So it's doing exactly what I'd ideally like a sensor to do, is to give me exactly what my input is, just some scaled version of it.